Can you trigger a chemical reaction without heat? I mean, think about it for a second. If you close your eyes and picture a chemistry lab, you're almost certainly imagining open flames, bubbling vats of boiling liquids, right? Just intense thermal energy. For centuries, that's exactly how we've been taught to overcome the activation energy required to force a chemical reaction. But what if we completely remove the heat? Picture a heavy metallic ball mill. Inside, a mechanical ball is violently grinding a raw powder. There's no fire, no boiling liquid, and yet, right before our eyes, that powder is transforming into an entirely new substance. It turns out, boiling liquids and intense heat are absolutely not the only ways to do chemistry.
Okay, let's dive right into this. Welcome to this explainer on a truly fascinating and innovative field of science, mechanochemistry. Or, as we like to call it, the architecture of physical force. We're going to explore how we can solve traditional, age-old chemistry problems, not by cranking up the temperature, but by utilizing raw physical power.
Here's our roadmap for today. First, we'll look at beyond heat physical force. Second, the Evans-Polanyi perturbation. And finally, green chemistry and sustainability.
So, let's get into Section 1, Beyond Heat, Physical Force.
On one side of the ring, we have thermal activation. This is the old way, the traditional way. It relies entirely on applying heat to a substance to give the molecules enough energy to overcome what's known as the activation energy barrier. But on the other side, we have mechanochemistry. Instead of thermal energy, we're using direct physical force to get the exact same job done. We are literally bypassing the need to heat things up altogether.
Now, what's genuinely surprising here is just how, rudimentary these actions sound. When we talk about driving complex chemical transformations, words like squishing, rubbing, and grinding probably don't sound like high-level science, do they? But honestly, that is the absolute genius of mechanochemistry. We're using incredibly straightforward physical actions, like the heavy grinding of that ball mill we pictured earlier, to literally force molecules into reacting. We are squishing them, rubbing them, and grinding them together until the chemical bonds essentially have no choice but to change.
Moving right along to Section 2, the Evans-Polanyi perturbation.
We're transitioning now from the macro world of physical grinding down to the fascinating micro world of molecular energy. And look, I know that Evans-Polanyi perturbation sounds like a super dense, heavy scientific term, but it's actually quite beautiful when you visualize it. I want you to imagine a physical hill. In chemistry, that hill represents the potential energy surface, or PES. In order for a reaction to happen, your molecules have to climb all the way up and over that massive hill. Normally, heat is what gives them the energy to make the climb. But the Evans-Polanyi perturbation explains how mechanical stress acts as a perturbation, basically a disruption on that surface. So instead of giving the molecules energy to climb the hill, we're physically altering the hill itself.
So the absolutely crucial point here is how this works step by step. Step 1, we apply physical pressure, represented by the letter P. Step 2, that pressure literally changes the activation volume. Actually, you can think of this mechanical force kind of like a bulldozer. It's literally stretching out and bulldozing that potential energy surface, which leads us perfectly into Step 3. By stretching the surface and changing the activation volume, we effectively lower the barrier for the reaction. We've bulldozed the hill down so low that chemical reactions that normally wouldn't happen without extreme heat can now happen with just a little physical force.
And that brings us to Section 3, green chemistry and sustainability. Okay, let's zoom back out to the macro level for a second. It's deeply fascinating to understand how activation volume and energy surfaces work on a micro scale, sure. But we have to ask ourselves, why does this matter to the real world? Well, the environmental payoff of this science is absolutely massive. Because we're using physical force to stretch that potential energy surface and lower the reaction barrier, mechanochemistry often requires absolutely no solvents. Solvents are typically required in thermal chemistry to dissolve substances and help the reaction along, but here, they just aren't needed. This lack of solvents makes mechanochemistry a foundational pillar of what's known as green chemistry. It gives us a highly sustainable, clean way to build entirely new materials and catalysts without the heavy environmental footprint of traditional labs.
Absolutely no toxic liquid waste. I mean, think about that image of a traditional chemistry lab again. The bubbling vats, the chemical byproducts, the highly specialized disposal required for all those liquid solvents. Now, picture a clean lab using mechanochemistry. By removing the need for extreme heat and harsh liquid solvents, we completely eliminate toxic liquid waste from the equation. That is a real game changer. This is the true promise of green engineering. We can still achieve incredible chemical transformations, but we can do it in a way that truly respects and protects our environment.
So, we've moved from a macro ball mill grinding powder down into the physics of bulldozing molecular energy hills and right back out to the creation of perfectly clean, sustainable laboratories. Which leaves us with this final provocative thought to consider. What other industries could be completely revolutionized if we stop relying on heat and toxic solvents and just start applying a little physical pressure? If squishing, rubbing, and grinding can rewrite the basic rules of chemical reactions, the applications for a sustainable future are truly limitless. Thanks for joining me for this explainer, and remember to keep asking the big questions.